Okay, we're going to take a look at potential energy and how that's related to conservative forces. All right, so what is a conservative force? Well, conservative force is any force that doesn't dissipate or add energy to the system through some outside conversion. Like, for instance, friction is a non-conservative force. It converts mechanical energy into heat. If I apply a force onto an object, that's a non-conservative force, because if I'm pushing, I'm using my muscles, so I'm converting chemical energy into mechanical energy. So with a conservative force, it's a force that if the work is done and we move the object between two different points, we can get that original energy back by simply reversing the process, reversing the path. So the work really only depends on where I start and where I finish. Well, the most common types of potential energy that we'll talk about is the gravitational potential energy. So, you think about going up a hill, it takes energy to go up the hill, or it takes work to go up the hill. You can certainly get that work back as you go down the hill. We'll also see that elastic forces, forces that obey Hooke's law, are also conservative forces. So once again, we know that the work done on an object between 2 points going from A to B is equal to the integral F dot dr. Okay, so basically, if we can think of a force is going to add energy to an object. Maybe it'll turn into kinetic energy. Maybe that energy will be dissipated by a non-conservative force. But if something does work on something, it is taking energy from it and putting it into whatever it's pushing. So if we're going to attribute potential energy to this force, we have to say that the change in potential energy's got to come from someplace. The change in potential energy is equal and opposite to the work that it does on the object. That's just basic conservation of energy. If the energy is coming from someplace, potential energy, it's got to go someplace, and it's doing work on the object. So we can also say that while work is the integral of F dot dr, or if the force is constant in the direction of the force and the displacement are the same, it's just force times distance, the change in potential energy would be negative. Okay, negative integral F dot dr. Okay, or again, for a constant force, it'd be much simpler. U would just be equal to the negative of the force times the change in position, the displacement. Again, there your force and your displacement have to be going in the same direction. Okay, so it's just another way of handling work done by a force, and it's basically saying, well, instead of calculating that work individually by that force, we're just going to calculate a potential energy associated by moving from one point to another point. All right. So once again, we can think of when we do work on something, okay, we're adding energy to it. When we have the potential energy expended, turned into work, okay, as the potential energy goes down, that's going to be turned into other forms of energy. So, the best way to think about this really is to do work on anything by conservative force, our potential energy is going to go down as the work is being done. Again, conservation of energy. Now, let's look at gravitational potential energy. We're going to start with the simplest form. We're going to say, what is the potential energy near the surface of the Earth? We know that there are actually two equations for gravitational force, for weight. The first one that we looked at, sometimes we read it as Fg, sometimes we read it as W, was just mg, okay? That is a conservative force. Now, that was the approximation, again, only near the surface of the Earth. later on, we're going to look at FG in terms of, large distances away from, objects, like the sun, like the earth. There we would write F of G in terms of Newton's universal law of gravitation, which would look something like this. So that's the next thing that we'll look at, but let's stick with this first of all. Okay, so once again, we want to calculate the change in potential energy due to a conservative force. This conservative force, of course, is gravity. So once again, I take my force, okay, that's just going to be negative mg, why negative? Because it's going downward. And I'm going to take my direction. Now, here, why do I choose dy? Think about that. Remember, it's f dot dr. So I only want to take the part of the displacement in the direction of the force. That's what the dot product really is taking here. So that dr becomes dy, and we can take constants out here. The negative m can go out front, the g can go out front, and we're just going to be left with the integration of dy. And again, for those of you who've done any calculus, that's a pretty easy integral to do. That integral is just, come on, erase. My iPad's a little slow today. But in any case, when we take the integral of dy, that just becomes the difference in y. So basically, it becomes the y, the height at position B minus the height at position A. Okay, so there is our equation for the change in potential energy due to gravity near the surface of the Earth. It's just mg. Sometimes we'll write delta y as h, but it's just mg delta y. How does our vertical distance change? Now, with gravitational potential energy, when we use this simplification, when we use this near the surface of the Earth, there's no absolute zero value. There's no place where the potential energy is always zero. Okay, we'll see that's not the case when you do the other thing. So this change in gravitational potential energy is really relative. It's relative to some point of interest, that we end up choosing here. So normally when we do this type of problem with potential energy, we always want to choose a convenient point that we can call sort of the reference point, where we would say y is 0. So looking at the potential energy, mgy, that would be equal to 0. The fact of the matter is, later on we'll see that when we're talking about conservative forces, okay, attractive forces produce negative potential energy, okay? We get that because basically, again, you saw the change in potential energy is equal to negative W, all right? And work is force times displacement, or actually F dot dr integrated. So when the force is attractive, we're going to have a negative potential energy associated with that. All right, just keep that in mind for later on. So let's look at a book and try to understand its potential energy. Okay, I can describe its potential energy with respect to, let's say, the top of my desk right here. I have a little book and I hold it up there, okay? And I'll call the surface of my desk y equals 0. Notice what happens if I change my reference point to the floor. Now y is much larger. So that book, which hasn't changed its height, effectively has more potential energy, okay? Now I hold it outside the window, all right? Now look how big that height is. Basically, what is important here is that when we define potential energy using that potential energy equals mgy, we are doing it with respect to some reference point, okay? So if you're solving a problem, everything has to have the same reference point because everything has to be relative to that level in defining the potential energy, okay? If I were to try to solve for some system, in case A, everything would have a potential energy defined with respect to the height of the desk. In B, everything would have a potential energy associated with the height of the floor, height from the floor. And then C, of course, the height versus the ground. So be very careful when you do these problems that whenever you define your reference point, that's very, very important because that's going to determine the energy. And of course, we have to conserve energy. Okay. Again, it's all relative. We can move the delta if we set some reference point at 0. So here we're defining this potential energy as mgy. And again, a lot of times you'll see in problems we'll replace the y with h just in terms of height. And this is the height above whatever reference point. In this case, we chose the ground. So again, can be written in a number of different ways. Mgy, where y is the vertical distance, or mgh, where h is basically your vertical distance from the ground. Let's just show, how these different reference points can affect how we do our calculations. Now let's set the 0 point at B. So we're going to put the 0 point at B. We're going to call that y equals 0. And down here, that potential energy is going to be 0. Okay. So looking at the skier up here, okay, they're 10 meters above that reference point. So there, I would say that their potential energy, oops, I did that. I didn't want to do that. I'm trying to use U. I'm so tempted to use PE because that's the way that I learned it, but I want to stick with what the text does. So we're going to say in that case, the U is positive. All right. And we'll calculate the potential energy based on that position. Now, if I set the 0 point at A instead up here, okay, that would make the potential energy 0. What doesn't change, even when I change my reference point, is how the potential energy changes, okay? The delta U is going to always be the same as I go from point A to point B, as the skier goes down, okay? That doesn't change. What does change is how I define what UA is and what UB is. Okay, so let's just do this. Let's see what this looks like. Now, in the first case, I'm going to define the initial point and the final point, okay? So that's the first case right here. Initially, my potential energy is mgy, okay? I'm 10 meters above the bottom of the slope, and thus I have 5,880 joules of energy initially. As I go down the slope, I go all the way down to the bottom of the slope, my new reference point is 0. So my final potential energy is 0. See, there's that 0. Mg times 0 is always 0. So notice what happened here. I started with a positive potential energy right here. I ended up with 0 potential energy in the end. So my potential energy decreased by negative 5,880 joules. All right. And again, that makes sense. We're starting from a higher point where our potential energy is higher. As we ski down, we pick up kinetic energy. Some work is done by friction, but that potential energy is converted to kinetic energy. So therefore, if I'm losing potential energy, the change in my potential energy must be negative. Now let's do the reference point as the top of the hill equal to 0. Okay. Now, initially, if my height is up here, if I'm saying this is y equals 0, my initial potential energy, mgy, is going to be 0. So that's going to be 0 right there. My final potential energy is going to be, come on, where's my pen? UF is going to be mgy. The new y is negative 10 meters. Okay, so here's a negative 10 meters, mgy, negative 5,880 joules. Okay, so again, I'm doing delta here. I'm calculating the change. Final minus initial. Final was negative, initial was 0. Notice I get the same result. Regardless of how I set my reference points, as long as I'm consistent with my reference points, either setting y equals 0 at the bottom of the hill or y equals 0 at the top of the hill, the change in potential energy is going to be the same. Okay, so whenever we're calculating gravitational potential energy with respect to the surface of the Earth, and we're using what's really an approximation, okay, as long as we're consistent with our reference points, we'll be perfectly fine. Now, what if we use Newton's universal law of gravitation? Okay, instead of using the simpler, let's get rid of that. Instead of using the simpler form of F equals mg, or if you're more comfortable, some people just like writing W equals mg. Okay, that's a real nice approximation for near the surface of the Earth. We're going to use Newton's full, we actually use the full vector form. And just to remind you what this is saying is, our force F is equal to G m1 times m2 over r squared, and it points to the center of our coordinate system. I was thinking that we should have a negative there, but okay, let's go ahead with doing this calculation. All right. So it's pointing toward the center. So now I'm going to calculate the change in potential energy. All right. This potential energy, instead of setting it to some reference point, says that if something is free and is unbound, it has 0 potential energy. Okay, so I'm going to set that as 0. Now, if I integrate this equation right here, okay, I get F right here. Here's my F. All right, R and dr, pointing in the same direction. They're going to basically give me 1. So I'm left with, unit vector r dot dr just gives me dr, which is a scalar. Okay. I can take all my constants out front. I'm going to take all of these out front. These are all constants. And I'm going to integrate 1 over r squared dr. Okay. And as I do that, I get this expression right here. So here's the thing. If I'm integrating from r to infinity, okay, I'm comparing how much energy it has compared to something that's taken an infinite distance away. I will get essentially this equation right here, okay? Because if I put in infinity in the denominator, that's basically 0. Subtracted by this r is really our original r. And again, I get this expression right here. So when we're talking about large enough distances where we are talking about the potential energy between 2 planets, or I don't know, a satellite on a planet, we want to use this form right here. And again, what you notice here is if you actually graph this, if you graph this, we'll look at this later, okay? We'll graph potential energy as a function of radius. Here's potential energy, here's radius. This has a discontinuity, actually goes to negative infinity as r approaches 0. So this is what it would sort of look like. Okay. Of course, we'll see that all objects have some radius, so we have to even make a modification to that. So again, not so important early on, but if we have an attractive force where like gravity is pulling two objects together, the potential energy is going to be negative, okay? And the way to think about this is I have to apply force, I have to put work into this to break free of this gravitational field, all right? And the more work I have to do to free it, okay, the more negative this potential energy is. So again, anytime we have an attractive force, it's going to be associated with a negative potential. And for gravity, since gravity is always attractive, when we use that formula, U equals negative G, M1, M2 over R squared, we're always going to get a negative value. Now, for repulsive forces, the potential energy is actually positive, okay? And two objects that are repulsive, you're never going to have them bound together. So you actually have energy associated with the two trying to push one another apart. All right. But again, generally, when we look at potential energy in any physical system, if it's a bound system, it means that it's bound by an attractive force, and the associated potential energy is going to be negative. All right, let's do the elastic potential. Let's do the potential of a spring. All right, so here is Hooke's law. This states that the force due to a spring is equal to the spring constant times the displacement from equilibrium. And of course, there's a negative sign there to indicate that as I pull it one way, the force from the spring is going to pull in the opposite direction. Okay, so I take this and I put that into my little equation right here. All right, probably simpler just to think of, yeah, this is a vector, this is a vector, just the scalar form of this right here, because actually the force is along the x direction, and therefore we'll replace dr with dx. So I have negative kx dx, okay? The potential energy is equal to the negative integral, just the opposite of what I'd be doing for calculating work. I calculate the potential energy compared to equilibrium. When x equals 0, that's the equilibrium, okay? And when I do this, I find out that the potential energy due to a spring, if I take the integral of x, the integral of x is x squared over 2, and that gives me this equation right here. Okay, so there's my potential energy due to a spring. Okay, now if you're not used to calculus, going from here to here might not be something that you have been exposed to. It's a very easy integral to do once you're familiar with calculus. But let's look at this a little bit of a different way, okay? Keep in mind, our potential energy is 1/2 kx squared. Now, if I graph F, which is equal to kx, I'll ignore the negative for now because this is the force that I actually have to apply. The area underneath the curve, which of course is an integral, it's a triangle, right? So down here, the base of the triangle is x, and the height of the triangle is kx. Now, what is the area of a triangle? Okay, base x times height kx times 1/2, because we take 1/2 the base times the height. So that is equal to 1/2 k, x times x is x squared. That's exactly what we got from the integral here. Okay, so that's another way of looking at this. You can actually do this graphically, where you can determine the area based on the shape of the force graphed versus the displacement. Okay, that's what the integral is. Find the area underneath the function, and again, you get 1/2 kx squared. So what are examples of conservative forces? We saw already that gravity is a conservative force, that U equals mgy, or U equals negative g m1 m2 over r squared. We saw that's true for spring forces. U is equal to 1/2 kx squared. But in physics too, we'll also see the same thing for electromagnetic forces. Okay, the electric force. Oops, I made a mistake here. I'm writing Newton's universal law of gravity instead of the potential energy. Should be an R there. We get the same thing for the electric force. The electric force is equal to K Q1 Q2 over R squared. So when we write a potential energy for it, it has a very similar form to what we saw for the gravitational potential energy. Okay, so basic fact here. We can assign a potential energy to any conservative force. For this course, mainly the ones that you're going to be dealing with is potential energy due to gravity near the surface of the Earth and the potential energy of a spring. Potential energy is associated with the position of the object within some system. So the potential energy is a property of the system, of course, and not the object. If you take an object and you put it in a different system, you can have a different potential energy. For instance, what your potential energy is on Earth 1 meter above the surface is going to be different from the potential energy of an object 1 meter above the surface of the moon or above Mars. Okay, let's do some calculations here. Potential energy, again, it's a mechanical energy from gravity. We know that work equals force times displacement. Okay, if the force is constant and the weight is constant near the surface of the Earth, and the displacement is near the surface of the Earth. So here, again, the potential energy is a work that gravity can do due to its weight and its height. So for instance, one application of potential energy is a wrecking ball. It's basically a large pendulum, and we swing this ball back and forth. And as we swing it back and forth, we're storing more and more potential energy. And as it swings down, all this potential energy is then turned into kinetic energy. The kinetic energy can do work, and it can knock the building down. So again, the crane swings in one direction. It's doing work on the ball to add more and more potential energy. And on impact, all that potential energy is suddenly turned into work, and this destroys whatever structure, demolishes whatever structure we're trying to take down. Now, a wrecking ball, typically, which is used in demolition, can have a range of weight from 1,000 pounds to about 12,000 pounds. That translates to a mass of 450 kilograms to 5,400 kilograms. Let's say we have a 5,000 kilogram wrecking ball, and we're able to swing it up 60 feet into the air, roughly 60 feet, 20 meters, how much energy is this going to have? Okay, now we put the mass times acceleration of gravity, that is the weight. You multiply that by the height, that's 20 meters, and we get roughly 1 million joules of energy. So this thing comes smacking into the side of the building. That's the same energy as a pound of TNT. Okay, so without the expense and the danger of using explosives, you can have essentially the same impact, no pun intended, probably even more because you can direct the energy so much better as using a single pound of explosives. And again, just think about potential energy, okay? You're at the bottom of the hill biking. What are you doing? You're putting work into the system. Where's the work going? Well, it's not necessarily making you faster as you're going up the hill, but it's being stored in the form of potential energy. Once that potential energy is stored, you can then accelerate down the hill as the potential energy is turned into kinetic energy. Almost all winter sports are based on converting potential energy into kinetic energy and trying to lose as little work due to friction as possible. Now, this ski jump was used during the 2018 Olympics. I can't remember where they were located, but you can see this is obviously not during a competition because there's nobody in the stands. But the whole idea of a ski jump is to give the skier a large amount of initial potential energy so that once they go off the ramp, that potential energy has become kinetic energy. They can, go as far as they're able. Okay, they basically become a projectile. And here you can see the top of the ski slope here. That's where we were looking down. And then you can see the slope where they're going to land. So again, basically what's happening here is you accelerate down, okay, accelerate down the slope, turning potential energy into kinetic energy. And then at the end of the slope, it basically you just become a projectile. And the more horizontal velocity you have, well, the more kinetic energy you have, the further you're going to be able to travel. There's some aerodynamics involved in here too, but for the most part, we're converting potential energy into kinetic energy. Now notice the landing slope is actually curved, almost has sort of a parabolic curve to it. So it gently comes up to the skier as the skier is going down, if you're using relative position. But as you can see here, the Olympic ski jumps are anywhere from 90 to 120 meters above the end of the ramp. And that's pretty significant. You calculate your energy here. For an 80 kilogram person, multiply that times the acceleration of gravity. The 120 meter slope gives the skier an incredible amount of potential energy, 94,000 joules. So as it go down again, all this energy is going to go from potential energy. Some will be lost due to friction, but that'll be converted into kinetic energy. Bobsleds, luge, skeleton, they're all sort of designed the same way. At the top of the track, you have higher potential energy. At the bottom of the track, that potential energy has been converted into kinetic energy. So this is from the 2002 Olympics. As gravity does work on the sled, the potential energy is converted into kinetic energy. And really, even though they're on ice and the coefficient of friction is very low, much of the kinetic energy is actually lost due to friction and air resistance going down because they're going at such a high speed. During the 2010 Winter Olympics in Whistler, the 1.45 kilometer long track had a vertical drop of 152 meters. Okay. Now the maximum weight that you could have for this should be maximum mass. Look at me. Maximum mass is 630 kilograms. And look how much energy this translates to. Remember that wrecking ball that had almost 1,000,000 joules of energy? This is pretty close to that too. So 1,000,000 joules of potential energy are going to be converted into work due to friction and also kinetic energy. All that potential energy. And again, downhill skiing, same thing. Start at the top of the hill. That energy is converted to kinetic energy, and some energy is lost due to friction and drag. And essentially, you're powering these sports by doing work to take the competitors up to the top of the hill, and then go down the hill as the potential energy is converted to kinetic energy. Mountain climbing. Now, this is Mount Everest, and if you were to go from sea level all the way up to the top of Mount Everest, you would be climbing 8,848 meters. Of course, nobody does that, and you'd have to start from the Indian Ocean in order to do that. But the potential energy at the top of Mount Everest corresponds to about 6 million joules for a 70-kilogram person. Okay. Yeah, they're normally starting at a fairly high altitude. I don't know how high the base camp is, but typically climbers will acclimate at a lower base camp, and they will do several climbs up and down to help not only train for the higher altitudes, but also acclimate the body to brief stints of a low oxygen environment. Now, this is a great example of how potential energy works. Okay, let's say that we are near sea level, and typically near sea level, the amount of energy that my vitals take up maybe accounts for, hey, that wasn't supposed to happen. Maybe accounts for about this much of the total energy that my body's burning, right? So if you were mountain climbing and you were pretty close to the sea level, oxygen would be fairly high. You'd be able to utilize your full metabolism, and therefore you'd be able to use all this energy up here to do work and climb higher and higher. Okay. The problem is I also need to keep myself alive by breathing, having my heart go, and just even my central nervous system takes up energy. Now, as I go higher and higher, the amount of available energy becomes less and less. Maybe at a slightly higher altitude, like around Denver, where the air pressure is lower, if I go on a hike, I'm going to feel more winded because, I have less excess energy. Sorry that those two red squares aren't equal, but unfortunately, it's just the way that I drew it. Mount Everest actually is at such an incredibly high altitude that the amount of excess energy you have left over compared to the amount of energy that you have to keep yourself alive, it doesn't leave you very much to actually climb the mountain. And that's why this is so incredibly dangerous. You hear of people getting frostbite because they can't generate enough heat to keep their exposed surfaces from freezing. You hear people getting, basically getting altitude sickness. And again, if you think about this, and in terms of energy, when we do work, that work has to come from someplace. At lower altitudes, we have plenty of energy that we can produce via metabolism, okay? But as we go higher and higher, that available energy becomes less and less, and the amount of work that we can do beyond just keeping ourselves alive becomes less and less. If you want to exercise, a great way to exercise is to climb stairs. The reason for this is you have to do work, right? Again, you have to exercise. And if you think about a 70-kilogram person climbing about 6 stories, that's about 18 meters. The potential energy gain is about 12,000 joules, okay? You know, in terms of converting that to food calories, like food calories, roughly 4,000 joules is equal to 1 food calorie. So you burn off, what, like 3 calories? But again, you got to remember that the energy here is coming from a lot of different places. First of all, as you climb stairs, your heart rate, your respiration go up, so there's more energy spent there. The muscles are not 100% efficient. In fact, climbing stairs are probably closer to about 20% efficient, so you burn energy there. But this shows sort of where that energy is coming from. You have to do work to climb the stairs, and this work is stored as potential energy.